Okay, great. Hopefully other people will be joining us in a minute, just as I speak. Okay, so let's continue talking about infinity, countable infinity versus uncountable infinity, and then we'll actually get on to what a topology actually is. Okay, so last time we talked about a nice criterion for when something is countably infinite, mainly, what is this on? This was the idea that if a set is countable, then we can get a surjective function from the positive integers onto that set, or we can get an injective function from the set onto the integers. So remember, if you have like a surjective function, that kind of implies that the domain is bigger than the range, because it's going on to the thing. So surjective means that the domain is bigger than the range. And if you've got an injective function, that kind of implies that the range is bigger than the domain, because you've got a bijection actually to a part of the set that you're going into. Okay, so as a corollary to that, we've got that any subset of a countable set is going to be countable. And that's true because if you've got a set that's countable, then you have an injection from that set into the positive integers. And then if you just restrict that to your subset, that's also going to be an injection into the integers. So straight away we get that the subset of a countable set is countable. And that's good, right? Because that is what we're thinking about size. That if something is a subset, it should be kind of could be smaller. But of course, the paradox of countable infinity is that an infinite a proper subset of a countably infinite set is going to be the same size. It's also going to be countably infinite. But the main thing is it can't be bigger. This also gives us a second proof for why the Cartesian product of the positive integers with itself is countably infinite. So remember, when we looked at it yesterday, or on Monday, we actually constructed a bijection from Z plus cross Z plus to Z plus. But we could have proved it directly with that theorem because all we've got to do is come up with an injection and that will do it for us. And a nice one could be something like 2 to the n times 3 to the m. Okay, so that is an injection from Z plus cross Z plus to Z plus. Why is an injection? Well, if 2 to the n, 3 to the m equals 2 to the p, 3 to the q, for example, what can we do? Well, let's say that without loss of generality, let's say, so if they are different, then one of them has to be bigger. So let's say, for example, p is bigger than m. Then 3 to the m equals 2 to the p minus n times 3 to the q. But of course, this side is divisible by, this side is not divisible by 2. Right, because it's just powers of 3. So therefore, we can conclude that p equals n. And so that means 3 to the m equals 3 to the q. And that implies that m equals q. And of course, you could have done it the other way. You could have done the 3's first and then goes on to the 2. Okay, a nice thing. The set of positive rational numbers is countably infinite. Okay, well, the reason why we can do that is because we can do a surjection from z plus cross z plus to the positive rationals. How can we do that? So, yeah, we can just look at the ratio. So if we look at this map by n, just taking it to m divided by n. That's what you were talking about, wasn't it? Yeah. Okay. This then is surjective. It's not. Why isn't it injective?
Because maybe it's not the lowest form.
Right. So 4,2 goes to 2,1 goes to 6. Yeah, so this map is not injective, but it is injective, right? Because every positive integer can be written as a ratio of positive integers, just like that. And then, so since we have that, and we know from before, since this is countable infinite, we know we have a surjection there. So therefore, by composing these two maps, we get a surjection from Z plus into Q plus. Okay. Countable union of countable sets is countable. Okay. So let's. How would we go about that? Oops. Sorry, people on the internet. I had the camera turned the wrong way. Anyway, a countable union of countable sets is countable. So, okay, so we've got a countable union of countable sets. So that means we have some sort of collection of sets. Each AN is countable and J is countable.
So we are not saying it's infinitely countable, right?
Sorry?
We are not saying it's infinite and countable, right?
Right.
We're just saying countable where we have.
So it could be infinite.
But you just put n, that's what I'm asking, because if it's infinitely countable, you cannot just put n. If you're.
So J is countable, so we can have. So I don't see what the question is.
Like, for example, Z is infinitely countable, right?
Yes.
And then we have just countables, finitely countable sets. So where are we saying here is finitely countable or just countable?
It's so remember, countable, it means either finite or countably infinite. So it's both.
It's both.
Okay. Okay. So that's our what we're given. So therefore, we want to show that the union is countable. So since it's countable, that means there exists a surjection for each set AN. So let's call that Fn. That goes from Z plus. So we've got a surjection for each set. And we have a surjection G that goes from the positive integers to our indexing set. Okay. And so now we want to define a new function h that's going to go from Z plus cross Z plus into the union of our sets. Okay, how are we going to define that? Well, we just set I've used J, haven't I? So let's say I and K. So what do we want to do it for? Okay, so what we're going to do is we're going to choose a map, and hang on, have I gotten this right? No, sorry. F G K of must be I. Oh no, hang on. G of I. K. Does that do the job? So it's well defined, right? So for any pair of integers, what I do is I use the first integer to choose one of my sets, and then the second integer chooses an element of that set. Okay, so it's well defined. Now, for it to work, it has to be a surjection. Is it a surjection? So what we want to do is we want to make sure that any element of any set is hit by H. Okay, why is that true? Well, any element of any set. Every set is hit, right? Because this is a surjection onto J, so this thing here goes through every possible index in J. Okay, and then K goes for a fixed I. K, then this is a surjection onto AGI, whatever that is. And so it goes through every element of that set. So it goes through every set, and in each set, it goes through every element of that set. So this is a surjection. And again, we do our trick from before. We actually need a surjection from Z plus to there, but we have our surjection, let's call it phi, from Z plus to Z plus cross Z plus. And the composition of these two things, phi and H, then goes from Z plus to our union. And so we're done. Okay.
Is there any way of doing this by contradiction?
Sorry?
Is there any way of doing this by contradiction? Assuming that it's maybe uncountable, then you can say that it must have a subset that's uncountable.
No, that sounds too difficult. I don't think that will work. So this is
too many details that I think it's uncountable. So how to partition to different subsets.
Yeah. I don't think you need to do that by contradiction.
Yeah, it's just too many details.
Because you assume that it's uncountable. Okay. Well, what does uncountable mean?
Like saying, like
That there is no. So you're saying there is no such that there is no. I mean, it's like, yeah. The logic of that sounds.
No,
like,
the thing is, like I was thinking, maybe if I say it's uncountable, like there's like it must have a like subset that's uncountable too, and like the building this union with countable things. So when we are saying that there is uncountable subset, then
yeah.
I thought like there's some sort of theorem that tells us about something about this uncountable.
Well, we haven't gotten there yet, so I think that sounds doesn't sound good to me. Let's do Cartesian, the last one. A finite product of countable sets is countable. So this time we are finite. Okay. So instead of that, we have got A1, A2, AN. We've got a fixed number of countable sets, each AI countable. And so we're going to do an induction proof. And so let's do it for well, let's actually just do it for 2. Okay. So let's say A cross B, and let's assume non-empty. Because if one of the sets is empty, then we do a Cartesian product, we get an empty set. So that's true. So we get a surjective map onto A and a surjective map onto B. And so if we glue them together, we get a surjective map from Z cross Z plus cross Z plus to A cross B just by, well, what are we going to do? H of IJ equals F of I G of J. Okay. That's basically surjective by construction. Okay, so since F and G hit everywhere in A and B, their Cartesian product's going to hit everywhere between A and B. That's surjective. And again, we've got the fact that we've got a surjective map from Z plus to Z plus cross Z plus to show that we have a surjective map from Z plus onto A cross B. And then, given this situation, well, each set is countable, then we just do the induction, right? So we assume it's true for up to n minus 1. Well, then we've got A1 cross A2 cross AN minus 1. That is going to be a countable set, and then we cross it with AN. And so that's just the Cartesian product of 2 countable sets. So it just follows from induction. Okay, so we've done some countable sets. Let's do more interesting, what's some uncountable sets? And so here are 2 examples. So from before we saw that a finite product of countable sets is countable. We deliberately ignored the countable product of finite sets for the reason that that's uncountable. So this set here, so let's let X just be the 2 element set 0, 1. So it's the simplest non-trivial finite set. And so if you look at its Cartesian product, its countably infinite Cartesian product, so this is omega. So given any set X, an omega tuple X is a function that goes from Z plus to X. Okay? And the set of all such tuples is X to the omega, and that's the countably infinite Cartesian product. Okay, so it's a set of all these functions from Z plus X. So you can think of it as a infinite tuple. So 1, you've got x1, x2, x3, x4, all the way up to x. like a sequence. Yep.
Okay.
So that's another way of thinking about it. But we're thinking of this as so you can think of it as the set of sequences. Yes.
They're all
So the I guess we can say that there's a bijection from the set of sequences to the countably infinite Cartesian path. Okay. So how can we show that this is an uncountable set? So now we've got to argue by a contradiction. Or maybe it's simple than that. So basically what we're going to show is if we have a function from the positive integers to our Cartesian product, we're going to show that it cannot be surjective. Okay. So, and remember from our criteria from before, this is enough to show that it's uncountable. Okay, so since we have this function, then we can have a look at g of n. And it's going to be, what's it going to be? So n is here, g of n is over here. So this is going to be a sequence of zeros and ones. So let's call that xn1, xn2, xn3, etc. Okay. So any map from here to here gives us a sequence. Okay. Let's define y and we want it to be an element of this Cartesian product, so it's equal to y1, y2, etc. by the following thing. So y kind of depends upon g. So the y comes from g, and what it's going to be is y of n is going to be equal to 0 if xnn equals 1, and it's equal to 1 if x00 equals 0. Okay, so given a G, which is a map from Z plus to the sequences, so G1, G2, G3 is each, so this is a sequence of sequences, and we're defining Y, which depends upon G, to be following this. And the observation then is that Y is not in the image of G. And if that is true, then G cannot be surjective. So what we've done is we've constructed an element in this Cartesian product which is not in the image of this function here.
So 1n is 0, and n is equal to 1. And the last element, it's nn, right?
Sorry?
1n.
This here?
Yes.
That's nn, yes. So, and we just go through, right? Well, so the question then, does y equal to some g of m, for instance? And you can just go through, well, it can't be g of 1, right? Because y1 is the opposite of what G1 of 1 is. Can't be 2 because it's the opposite of what G2 2 would be. It can't be 3. And so by induction, we go through the whole integers and we see that this is, by construction, it's not in the image of that function here. So it's not a surjection, so it's uncountable. Really clever little group. I think Cantor was the first one to come up with this argument.
It's really close to, it's same basically with diagonal argument, right?
Yes. And so this is a very famous argument in set theory and logic that's used all the time. I think Turing came up with a similar thing about something not being computable, doing some kind of similar type of argument. So this is a kind of a famous argument.
Yeah, he basically mapped all theorems to natural numbers and said that there are theorems that are unprovable, although they can be true.
So, yeah, it's something about computability. Yeah, exactly. Okay. The second thing, power set. So remember what the power set is? So given any set X, the power set of X is the set of all subsets of X. And it's just denoted P of X. And the power set of the positive integers is uncountable. And that follows from the following theorem that A be any set, there is no injective map did I forget to put a no in there? I believe that's a mistake, isn't it? It should be no. It should be no. Okay. And there is no surjective map from a set to its power set. Okay. And again, if we think about injective sets, injective maps, if you have an injective map, then you think of this thing as somehow being able to fit inside that thing. And if there's a surjective map, then you kind of think of this thing covering this thing. And so, so this follows directly from, as a corollary of this theorem. Okay, so let's prove that.
Theorem 7.8.
This is theorem 7.8 in the book.
To prove theorem 7.8 or
yeah, we're going to prove theorem 7.8 because once we have theorem 7.8, then this follows as a corollary straight away, right? Because that means there is no injective map, there's no surjective map from Z plus to the power set of Z plus. Okay.
My first equation to this proof is like, can we reason with singleton first? For example, any subset has a singleton, and we can map first all our A to singleton.
So I don't know exactly what you're saying.
You know, singletons, subsets, like each subset has at least singletons. So
yeah, there is a natural map. That's a so there is a bijection between A and the singletons of A. Yes.
Yes. And then after that we have other subsets too, and you can just say.
No, I don't like the way you're thinking. Okay. Now, we actually only have to prove one of those statements because of the following fact that we've kind of already noted, that if B is non-empty, then the existence of an injective map goes from B to some set C implies a surjective map G that goes from C to B by just defining G of C to equal some F inverse of C if C is in the image of F and arbitrary otherwise. Let's say equals sum. No. Since it's injective, there's going to be a unique element that it comes from. Right? So see if we've got an injective map here, we can pull back and there's going to be some part of C which is going to be in bijection with B, and then anything else we just make it arbitrary to some other element. So that's why we need the set to be non-empty. So that we've kind of seen that before, so that means we only have to prove one direction. And which direction do we want to show? We want to show the surjective one. So given a function from A to the power set of A, we want to show it can't be surjective. So let B be the subset of A defined to be let B be the set of all elements A in A such that A is not an element of G of A. Okay, so we've got this. We're given this function G, and we just look at those elements A such that A is not in its own. It's not in its image. Okay. Now this is a subset of B. So B is a subset of A. And I claim that B is not in the image of G.
We can suppose that this element that maps to B, then we can prove that.
Right, because if A is an element of B, then by definition, A is an element of A without this, take away the element. But G of A is B. So we've got A is both an element of B and the complement of B. And that's our contradiction. Another really, so we had to wait to uncountable to get to the really cute proofs. Like all the stuff before was pretty boring, but uncountable stuff is pretty fun. Okay. Let's get on to topology, finally. What is a topology? Well, you've probably heard of things like topology is rubber sheet geometry or something like that. So in geometry, we're concerned with points and lines and planes, sort of like the relationships that points have in some space. Topology is kind of like we're interested in a point, and we're kind of interested in things that surround that point, and somehow they get bent into something else. And that's the idea of rubber sheet. So what we've got to do is we've got to look at sort of like neighborhoods of a point. So this is what we're doing here. So a topology on a set X is a collection of subsets of X having the following properties. So the empty set and the entire set are in the topology. The union of the elements of any subcollection of the topology is in the topology. And the finite intersection of any subcollection of sets in the topology is in the topology. So arbitrary union, finite intersections. It's closed under that. And the set X for which a topology has been specified is called a topological space. Really, we should talk about X and the topology because a set can have more than one topology. Now, the elements of the topology are called open sets. Okay, and then all of a sudden this should make sense, right? Because an arbitrary union of open sets is going to be open, but only a finite union of open sets is going to be open. Because if you can have an infinite, say the collection 0 to 1 to n interval. If you look at the infinite union of that, you'll get, well, you can get, no, minus 1 on n to 1 on n. That open set, take the infinite intersection, you get just the point 0, which is closed. So you need, this is important. So as I said, there can be more than one topology on a set. And so if one topology sort of contains another, so that the collection of open sets is contained within another collection of open set, if this is bigger than that, hang on. Did I do this right? I'm wondering if I did this correctly. Right, because I was just copying down. Oh, I got this wrong. Sorry, I'll correct this. That doesn't make sense, right? It's if T prime contains T, then we say that this is finer and this is coarser. So if it contains it, there's more open sets, and so we've cut up the set finer and finer.
The larger is finer.
The larger is finer. Yes, I made a mistake there. And either way, we say they're comparable if one is contained within another. So it's possible to have topologies that are incompatible. Other words you might hear are things like larger or smaller, and weaker or stronger topologies. Weaker and stronger is, we won't be using that because in some books, people use opposite definitions of weaker and stronger. So analysts and topologists use different definitions of weaker and stronger. One for them is weak, for the other is strong. That's just because they're different fields. So we won't enter into that confusion at all. Okay, so here I've got a 3-element set. Which of these is a topology? A, B, C, D. Or maybe more simpler, which are not topologies? Why is A not a topology?
Union is not union is not in our set, right?
Sorry, which one? Sorry?
A1, the union of these two sets.
So these are four different topologies, four different collections of sets. So this one here, the open sets is this, this, and the whole thing. Okay. Is this a topology?
No.
No, because it should have the union of these things. It doesn't matter that this doesn't have a set. So this is not. Is this?
Good.
It is, right? Because there, the union, well, that's the whole thing. The intersection or the empty set. What about this one? It's not. Why isn't it?
The intersection is not.
Right. There should be a little circle around here. And this is a topology. So what is the course? So how can we turn that into a topology? What would be the coarsest topology containing that? Just to include, to make that an open set. And for C, what is the coarsest topology containing that? Well, that would be just to include that one there. By the way, what's the time, anyone?
13, 12, 13.
Okay, good. So what's the coarsest possible topology? That would be if you've got a set and you just look at the collection just consisting of the whole set and the empty set. That is a topology, right? Because it's closed under union. X union empty set is X, and it's closed under intersection. X intersection empty set is empty set. Okay. That's called the indiscrete topology or the trivial topology. What's the finest possible topology?
Power set.
The power set, exactly. So the power set, where all the collection of all subsets of X is also a topology because trivially it's closed under union intersection, and that's called the discrete topology. And it's also not, it's not that useful. Right? It's not going to give you that much information. So here is a collection of all the topologies on a three-element set. Okay. So here we start at the trivial. And here is all the ones where we've just got one proper subset, one proper non-empty subset. Then we can go to the ones with two. Then here's with three, this one and this one, I guess. Then four, and then here with six.
Is there a closed formula for finite sets for number of topologies?
That's a good. Probably. I don't know what it is, but you can probably figure out, because like if there's one point, there's only one topology. If there's 2 points, well, the thing is, you only want to count this once, right? Right, because this guy is obviously a bijection with that guy. We'll talk about that, what that's called a homeomorphism. So, it's an interesting little problem to count the number of finite topologies. It'll grow pretty rapidly, I would think. Okay, so let's have a look at some maybe non-trivial topologies. Okay, so let's say we have a set. Let T sub F be the collection of all subsets of X, such that X minus U is either finite or it is all of X. and let T sub C be the collection of all subsets U of X such that X minus U is countable or is all of X. Then TF is a topology, finite complement topology, and TC is a topology, the countable complement topology. So let's finish off by proving that. Or just the first one. So why is that true? So we want to show that is a topology. So let's go through the three requirements. The first one is that X and the empty set. Okay, well, X minus X is what? It's the empty set, and that's finite. So that's true, that's in there. X minus the empty set is X, and that's in there too. So requirement 1 is done. Requirement 2 is what? Is that union, it's arbitrary union. Okay, so let's say we're given some arbitrary family of non-empty elements of our topology. Okay, I'm just assuming non-elements because if the elements are empty, then it's trivial. Because if you just add the empty set to anything, we don't really change it. So if if X is one of them, the elements in that collection, then we're done, right? Because when we take the union, we're going to get X, and so we're good. So let's assume then, assume that X is not in there. Okay, so what do we want interested in? We're interested in that union, possibly arbitrary union of sets. Okay, so what do we look at? We look at X minus the union of these sets. Now we've got to remember some set theory. So do people remember De Morgan's laws? So what does X minus a union equals what? So X minus a union of sets, so A minus a union of sets B equals what? We can write it as intersections, right?
Components. Intersection of components.
Yep. So that equals the intersection of time to go. But now we're done, right? Because since X isn't in here, all these guys are finite, and the intersection of finite sets is finite set. And I guess we need to go and I'll finish up this thing later, this thing on Friday. Whew. Stop recording.